All right, guys, Mr. Antonucci here, and this is section 8.3, volume of A Solid of Revolution. We're going to talk about disks and washers. Specifically, we're going to talk about the disk method in this video here. And to kind of get us started here, when you think about, we're trying to find the volume of a three-dimensional shape that's not one of the normal ones that we learn from geometry, like a cylinder, a cone, or a sphere. How about like a piece of fruit, like a pear, apple, lemon, or candy, or something like that? So we're going to look at a pear here, and suppose we wanted to find the volume of a pear. One of the things we could do is cut the pear in half and look at a flat piece of the pear. Okay. And a flat piece of the pear would kind of have like a sideways pear shape, like this. If we superimpose the top half of that onto a graph, you'd have the upper half of a pear. Now, just imagine with me if this was filled in, okay, and the boundary of the pear's outline could be thought of as a function. Okay, some function of x going to model that outline. We could actually get the area of that slice of the pear using calculus, just integrate the function over the interval. And how we get the volume is a similar process to how we got the area of a region. So the first thing we could do is take a vertical slice, okay? But instead of getting the area, what we're going to do is put a crank. Instead of getting the area of that rectangle, we're going to put a crank and rotate it. If you imagine rotating that little strip around the x-axis and filling it in as you rotated it around, you would get a circle. Okay. Now the area of that circle is pi r squared. Okay. Now the radius of that circle is the vertical strip right there. And the length of that strip corresponds to the function. So I could further refine this as pi times f of x squared. That's going to be the area of that little circle. Okay. Now, we could actually get the volume of that circle, thinking of it as a cylinder rather, because whenever you take that vertical strip, there is some thickness right here, and we'll call it delta x. So the volume would just be the area of that circle times the thickness of it, which would give us the volume of that one slice. Now, if you could imagine, we could take more slices and get the volume of that one, another slice volume of that one, and so forth and so on. And what ends up happening is if you get all of those slices, their volumes, and add them up, you get an approximation for the volume of the pear. So the volume of the pear is approximately the sum of f of xi squared delta x times the pi. Okay. Now that's going to give you the approximate volume. And we all know what to do. This is a Riemann sum. So if we take the limit as the number of representative circles approaches infinity, what's going to end up happening is the volume is exactly equal to pi times the integral from a to b of f of x squared dx. Another way to think of this is the function is the radius, the function that models the radius. So you think of it as the pi times the integral of r squared. That should be dx. Dx right there. So now here is the formula right here. Volume of a solid of revolution using the disk method. So same thing right here. Now what we're going to do is find the volume of the solid of revolution generated by revolving the region bounded by the graph of y equals square root x and the line equals x equals 5 about the x-axis. So if I just draw the region, Okay, so this is 5. And here's the graph of the square root of x. And this would actually be 25. No, it wouldn't. It would be y equals square root of 5 at that point. Okay, so this is our region. Okay, and if you think of a representative slice like this, rotating it around, it helps just to draw one so that we can see the shape here. So the volume is pi times the integral from 0 to 5 of square root of x squared dx, which is going to be pi integral 0 to 5 x dx. And then we take the antiderivative there, which is going to be x squared over 2 times the pi, evaluated at 0 and 5, and subtract. So if you plug 5 in, you would have 25 over 2 pi minus 0, which is going to be the answer. So this is 25 pi cubic units. Okay, so that's our answer right there. Not too shabby, huh? So notice the disk method does not require that the function be non-negative. So if you look up at the definition here, it doesn't say that it has to be non-negative. So if the function is continuous on the interval a to b, the volume of the solid of revolution obtained by revolving the region bounded by the graph of f x-axis in the lines a and b about the x-axis equals the volume obtained by revolving the region of the graph of y equals absolute value of x. And since the absolute value of f of x squared is the same as f of x squared, the volume formula does not change. And the reason I bring that all up is because our next example, what we actually have is a situation where part of the graph is above the x-axis and part of it is below, and we're still going to rotate and find the volume here. So we're going to do x cubed in the lines -1 and 2. So this just gives you our boundaries. So our region goes from here to here. Notice, okay, this little piece down here is below the x-axis, but what we're going to do is put a crank on this and turn it. And so we're going to have like a big kind of like horn shape here and a little horn shape here. And then we're going to get the volume of that solid. But no matter what, the radius, the function that models the radius is x cubed, and r squared is going to be x cubed squared, which is x to the 6th. And so even though this region down here has negative y values, when we square them or raise the x value to the power of 6, it ends up being positive. And that's what I was trying to say up here with whenever we square the absolute value of a function, it's the same as the function squared. Okay, so oftentimes it's very important to identify what the radius function is. So if you have the graph and you draw a vertical strip, that's going to help you see that the radius goes from the x-axis up to the graph, and the graph is bounded by the function x cubed. So the volume is pi times the integral of the radius function, so x cubed, squared dx, and we're going to go from -1 to 2. Okay, so that's pi integral -1 to 2 of x to the 6th dx, which is going to be pi x to the 7th over 7. And we're going to go from -1 to 2. And then what we would do is plug in 2, plug in -1, and subtract. So we would have pi over 7 times 2 to the 7th is 128, minus -1 to the 7th is still -1. So you end up with 129 pi over 7. And again, the units would be cubic units on that one. Oops. So next example we want to take a look at is the volume of the solid revolution about the x-axis generated by revolving the region in the first quadrant. So that helps us know that it's going to be in the first quadrant, bounded by the graph of 5e to the negative x, x equals 3, and both axes. So the actual region right here goes all the way up, but just to 3. Then you imagine you put a crank on the x-axis, spin it. So you take a representative slice, and you can see that it makes a filled-in circle. So the radius function is the function that produces the graph, which is 5e to the negative x. So the volume, we'll just do it down here, is going to be pi times the integral from 0 to 3 of 5e to the negative x squared dx. Now, how I got the limits 0 and 3 is because the region is in the first quadrant, it has to start at 0 on the x-axis. And then the other boundary is x equals 3 there. All right. So for this one, what we're going to do is first off, we'll square this. So if I square the 5, that's going to give me 25. So I'll factor that out with the pi. And you get 0 to 3 of e to the negative 2x dx. Now we know how to integrate this because we can use u substitution and pattern recognition. So since the u would be negative 2x, the du would be negative 2. We'd have to adjust for that by multiplying by a negative 1/2. So we would have negative 25 halves pi e to the negative 2x evaluated at 0 and 3. So you would have negative 25 pi over 2 e to the negative 6 minus e to the 0. Okay, so you'd have negative 25 pi over 2, 1 over e to the 6th minus 1. And when you simplify that all down and distribute it, it looks like the answer is going to be negative because you have this negative out front here. But be careful because 1 over e to the 6th is a very small number. Subtracting 1 gives you a negative, and then multiply by that negative 25 pi over 2. You're going to end up with 3 decimal places of accuracy getting 139, or excuse me, 39.173, and that's going to be the volume of that region there. All right. So I hope that one was helpful to you guys. Take care.